Right, so what have we got? I'm going to state Muirhead's theorem. Inequality. Well, basically, if I've got two sequences, A, which is A1, A2 up to AN, and B is B1 through Bn, and I know that A majorizes B, then if and only if, so A majorizes B if and only if the symmetric mean is greater than the symmetric mean of B. That's it. We need quite a lot to set up. We needed to set up the definition of majorization, which is this curly kind of greater than, and we also needed to set up what the symmetric difference was. And you sometimes see it written like this with an equality: if and only if symmetric mean exceeds or equal to the symmetric mean of B. Okay, so let's do some examples. Right, so let's try A as a sequence equals, let's try 2, 0, 0, and B as a sequence is 1, 1, 0. So we'll just check that A does in fact majorize B. Well, it does, because the sums are equal, they're both equal to 2, and the sums are both equal to 2, and the partial sums are the right order, because the partial sum of the first one's 2 is greater than 1, and the partial sum of the first 2 is 2, which is greater than or equal to the partial sums for B. Okay, so there it is. So what does Muirhead's inequality say? Well, it says that A is greater than or equal to B. Actually, it says it's greater than, because we know that A strictly majorizes B, but it doesn't matter. So what does that mean? That means that 1 over 3 factorial times sigma over all permutations of x1 to the A1, x2 to the A2, x3 to the A3. Just tell you where all these symbols are coming from. x1, x2, x3, x1, x2, x3, they're just numbers. They're just arbitrary positive numbers. Is greater than or equal to 1/3, or 1 over 3 factorial at least, sigma over all permutations of x1 to the B1, x2 to the B2, x3 to the B3. All I've done is written out the definition of the symmetric mean. And of course I'm going to forget the 3 factorial, because I don't need it. So what does that tell me? That tells me that, let me just pinch in a little bit and just remind myself what A and B are 2 and 1 and 1. So that says that the symmetric sum of x1 to the 2, x2 to the 0, x3 to the 0, because all I'm doing is taking A1, A2, A3 from A, is greater than or equal to the symmetric sum of, let's get this right, x1 to the B1, which was 1 from up here, from there, x2 to the power 1, because that was the second element of B, x3 to the power 0. Okay, and now I'm going to expand it. Goes to what? Well, we've got x1 squared. Oh, sorry, that should be x3. I'll write it out fully, and then you'll see how everything cancels out. x1 squared, x2 to the 0, x3 to the 0, plus, and then x1 squared, x3 to the power 0, x2 to the power 0, plus x2 squared, x1, 0, x3. Actually, it is quite a good idea. x2, x1, x3. It's quite a good idea to write in all the x's and then put the powers in afterwards. 3, 1, 2, 3, 2, x1, 2, 0, 0, 2, 0, 0, 2, 0, 0. So that's the left hand side. So the left hand side equals, you can see that it doesn't really matter the x2 to the power 0 and x3 to the power 0. When you swap those guys over, we've got 2 and 3 and 3 and 2. Because the powers are the same, it doesn't matter. So with the left hand side equals 2x1 squared from this one and this one, plus 2, no, I'm not call it y, x2 squared plus 2x3 squared. Okay, that's what the left hand side is. And I'm asserting that's greater than or equal to the right hand side, which equals, let's do this, that's sigma over all permutations, x1, x2, x3, and these are to the power b, which is 1, what was b? B was 110. Okay, equals, and then you go through the whole process again, and you observe that x1 can be swapped with x2 because they're the same power. So we've got 2 copies of all that, and so it's equal to 2x1 x2 plus x1 x3 plus x1213 x2 x3. So altogether we know that the left hand side is greater than or equal to the right hand side, because the sequence A, where was it? Here it is, the sequence A majorizes the sequence B. So the left hand side is greater than or equal to the right hand side, so that tells me that 2, I'll cancel the 2's out in a minute, oops, 2x1 squared plus x2 squared plus x3 squared is greater than or equal to 2 x1 x2 plus x1 x3 plus x2 x3. Okay, because this was the right hand side and this left hand side here comes from here. So cancelling 2's gives me x1 squared plus x2 squared plus x3 squared greater than or equal to x1 x2 plus x1 x3 plus x2 x3, or even x squared plus y squared plus z squared greater than or equal to xy plus xz plus yz. Now, I dare say you could have proved that theorem more simply without going through all this rigmarole of Muirhead's theorem. But there it is. I'll show you in the next couple of screencasts some more theorems which might be, or some more conclusions of Muirhead's theorem, which might be some more deductions from Muirhead's theorem that might be a bit more interesting. Okay, I'm going to stop there.